Hello, everyone. Welcome to today's live broadcast, Applications of Separation and Mass Spectrometric Techniques for Challenges in the Analysis of Per- and Polyfluorinated Alkyl Substances, or PFAS, in the Environment. I'm Laura Bush, the Editorial Director of LCGC, and I'll be your moderator for today's event. We're pleased to bring you this webcast presented by LCGC and sponsored by MacMod. A company should be able to condense its mission statement into a simple phrase. MacMod's mission statement is smarter chromatography. But you may ask, just what does smarter chromatography mean? It means that when they make a recommendation to you about an HPLC or UHPLC product, it's to partner with you to offer innovative solutions to your complex problems. They use advanced, state-of-the-art analytical software to match their product portfolio with your separation needs. They leverage their 30-plus years of experience in the LC column business, their technical expertise, and their manufacturing network to help you solve your toughest application problems. They provide up-to-date and accurate technical catalogs and reports from industry-leading separation scientists to keep you informed of new technologies. Before we get started today, we just have a few housekeeping announcements. The webcast is designed to be interactive, so we encourage you to ask questions. You can submit questions at any time by typing them in the Q&A box, which you can find on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the webcast. And if you have any technical problems viewing or hearing the presentation today, please click on the question mark Help widget in the dock at the bottom of your window. I would now like to introduce today's speakers. We are very pleased to be joined today by Charles Powley and Andrew Herron. Charles Powley has worked in the area of trace environmental analytical chemistry for more than 35 years, with specialization in GC, GCMS, LC, and LCMS. He is currently the Chief Scientist of the Stride Center for PFAS Solutions in Newcastle, Delaware, which is a nonprofit laboratory specializing in non-routine investigations into PFAS contamination. Prior to 2017, he worked for the DuPont Company for 32 years, with most of his career spent in developing analytical methods for PFAS and pesticide residues. From 2003 to 2008, he was a research fellow and manager in the bioanalytical group at the DuPont Haskell Research Center, where he developed and published several PFAS methods and studies. Chuck Powley received his Bachelor of Science degree in chemistry from Rensselaer Polytechnic Institute and his PhD in chemistry from the University of Illinois. He completed a postdoctoral assignment at the University of Georgia under the direction of L.B. Rogers before joining DuPont. Andrew Herron is an applications research scientist at Advanced Materials Technology, where his focus is on LCMS. Before joining AMT, Andrew was with Thermo Fisher Scientific as an applications scientist, focusing on HRAM and triple quad application and development. Previously, Andrew worked for the U.S. Department of Agriculture, where he focused on LCMS application development for co-products that are produced during the biofuel process. Andrew received his PhD in chemistry with a focus in analytical and mass spectrometry under Dr. Charles McEwen at the University of the Sciences, developing and adapting new methods of ionization for both large and small molecule applications. In addition, he served as a faculty member in the Department of Chemistry at the University of the Sciences and as an adjunct professor at Villanova University. Thank you both for joining us today. Chuck, please get us started.
Okay, thank you very much, Laura. And so here's our title slide, and this is jointly presented by Stride Center for PFAS Solutions and AMT. And so my title slide is the same topic, and I will get started with some introductory material. Here's a roadmap of where I'm going. Going to first talk a little bit about PFAS chemistry to give you an overview, and then in particular why PFAS analysis is so challenging. It is probably the most challenging area in trace level environmental analysis. And then I want to briefly go back in history a bit to tell you how the analytical tools involved, because just to explain why and give you some insight as to why we really didn't know this was much of a problem until the turn of the century when electrospray LC-MS was commercialized. And then spend most of the time on how the challenges are met. And there's challenges in sample collection, sample preparation, and analysis. So first of all, some caveats, assumptions, and idiosyncrasies. As you probably know, there's a lot of litigation going on in this area. I really do not want to be part of it. So there's going to be no finger pointing in my presentation to companies or products. I'm just going to focus on the science today. I'm going to assume that my audience has a good to excellent understanding of chromatography, particularly GC and LC, but maybe kind of a mixed bag on mass spectrometry. So I'll spend a bit more time explaining some mass spec problems and techniques than I might otherwise, and I hope the mass spec experts will bear with me. And then finally, I'll be saying PTFE in a lot of places where you might be saying Teflon. They are not the same thing. Teflon is a trademark registered to the Chemours Company now, previously to DuPont, for a whole class of nonstick products, whereas PTFE, polytetrafluoroethylene, is the polymer that I'll be focusing on. So first of all, bit of PFAS chemistry. Around the turn of the century, there was only PFOA and PFOS. So PFOA is known as perfluorooctanoate, perfluorooctanoic acid, PFOA, or C8. And then the sulfonate is pronounced as the sulfonate or the sulfonic acid or PFOS. Now, I'm going to be talking about short chain and long chain PFASs. So for carboxylates, it's less than or equal to 7 carbon units. And for sulfonates, it's less than or equal to 6. And then for the longer chain PFASs, greater than or equal to 8 for carboxylates, greater than or equal to 7 for sulfonates. So PFOA and PFOS are considered to be long chain PFASs. And the big emphasis in recent years has been moving away from these longer chain compounds to the shorter chain ones that I'll be talking about. But the longer chain ones are still with us. They do not degrade in the environment to any significant extent. So we're still dealing with them, seeing them, and they just keep getting pushed around. Once some problems started surfacing, we started seeing some replacements come into the discussion. For example, here's hexafluoropropylene oxide dimer acid, abbreviated HFPODA. You've probably heard it referred to as Gen X, and that is the compound that DuPont invented to replace PFOA in the PTFE manufacturing process. Another one is N-methylphosa, and here's the name of it. That is a PFOS precursor. So especially in industrial areas, you might see this in the environment, and then it eventually breaks down to PFOS where this group leaves. And then another important class of PFAS are telomeres. And you recognize a telomere by this ethylene connector shown on this slide here. And the 6,2-fluorotelomere sulfonate is a surfactant and also a degradant that we can see in a lot of environmental samples and problems, particularly where firefighting foams are used. And then here's a fluorotelomere alcohol here. This is an intermediate. It's also a degradant. It's volatile, so that gets into gas chromatography and is kind of beyond the scope of this talk. Estimated now there are 4,000 to 4,000 to 5,000 PFASs in the environment right now. And that is a humongous number. We will never be able to measure all of them. So currently there's only less than 100 for which we have authentic standards. A couple notes about PFAS process chemistry is that there are two major processes used to produce PFASs. The electrochemical fluorination process just takes a hydrocarbon, an acid chloride, and treats it with HF, an electrochemistry, and fluorinates all the sites. It produces branched isomers, cyclic isomers, and is kind of a messy process for that reason. That's the process 3M used. It is no longer used in this country, but still used in China. The telemer process was invented at the same time, and this is what DuPont and the other companies started working with. And in this case, you just take a tetrafluoroethylene, make it into an iodide, and then keep on adding ethylene units. The difference between the ECF process is that you end up with only linear isomers, and they are even numbers because you keep on adding even numbers of carbon units. And so these result in different types of surfactants, many different surfactants. So in the area of PFAS exposure, this is a slide that shows that industry manufactures them, and they show up in consumer products, which goes into the waste infrastructure. They go into the environment. They go into firefighting foams. All that ends up in the environment and into the waste infrastructure. And then eventually we get human exposure coming from both the environment, drinking water, and consumer products, clothing, that sort of thing. And there's transfer to infants even through breast milk and cord blood. So this is a cycle. It's a never-ending cycle because along this way, unless some of these PFASs find their way to an incinerator, they do not get destroyed. And so we keep on moving them around. That's why we call them forever chemicals. So briefly, humans ingest PFASs from drinking water and from the foods that they eat. The major source is now thought to be drinking water, but foods contain PFASs as well. You can get PFASs coming from wrapping papers, particularly some of the non-stick wrapping papers that you might find fast foods wrapped in. From wastewater treatment plants, the biosolids that are produced from these plants are sold or given to farms as a nutrient-rich source, and that can then find its way back into crops and end up mostly in meat and dairy. But sometimes it's applied to fruits and vegetables as well. So that's how we get a secondary exposure to PFASs. And then they biomagnify up the food chain. So lower organisms have certain PFAS levels. As it moves up the food chain to basically humans, those PFAS levels biomagnify. Known health effects from epidemiological studies where there was heavy contamination, low infant birth weights, immune system problems, prostate cancer, thyroid hormone disruption, all kinds of endocrine disruption problems, and increased cholesterol levels. So why is this so tough? Well, right now, with the way the regulations are set and with the level of concern out there, PFASs need to be determined in drinking water samples at part per trillion levels or 1 nanogram per liter levels. Part per trillion is about 3 seconds in 100,000 years. For the other environmental samples like unfinished water, surface water, groundwater, and human blood serum, part per billion levels are fine, but a part per million is a bumblebee in a football stadium, so that can be challenging as well. And then the biggest problem here, besides those low levels, is contamination. It's really easy to get samples contaminated or laboratory contamination and get false positive results. So PTFE components of instruments, as I'll show you, and of sample collectors. Sample containers can have PFAS contamination. Carpeting, upholstery, PFAS surfactants are used to make those. Nonstick foils and papers, as I mentioned. Clothing, here's a couple of clothing lines, Gore-Tex and Tyvek. Even cosmetics have some PFAS surfactants, and food wrappers and containers. If a lab gets contaminated, and they're trying to do trace level analysis, a bad contamination problem is virtually impossible to solve. You really can't clean up this stuff very effectively. You just pretty much end up pushing it around. Lots of times, the only solution has been to move to a different lab. So getting into the chemistry, there's two problems here. The first is that they're surfactant. So they're difficult to clean up because they don't prefer hydrophobic areas or hydrophilic areas. They really prefer the interface between the two. We see a hydrophilic head on PFOA, for example, that prefers water, and a hydrophobic tail that prefers soils and fats. And also, they're perfluorinated. So the nature of these things is they're not sticky. That's why they're out there being used. They show up in nonstick products of all types. So they won't stick to any type of cleaning agents like soaps. And then the carbon-fluorine bonds in PFAS are the strongest chemical bonds known. And through electronic interactions, also the carbon-to-carbon bonds in this hydrophobic tail are very strong as well, much stronger than your usual carbon-to-carbon bond. So you can't destroy them with bleach like you can with some pesticide residues. So going back in history, in environmental analysis, the early focus was on water and blood serum, and so we did PFOA and related carboxylic acids by gas chromatography. The detection was usually by electron impact quadrupole mass spectrometry, and here's a schematic of a quadrupole down here where you introduce your molecules, hit them with an electron ion beam. They're separated by a quadrupole ion analyzer, and the ones that make it through that are selected are detected. You would think that being loaded with fluorines, PFASs would be great on an electron capture detector. They are not. ECDs prefer big targets, so fluorines are very small and compact. And also, they prefer conjugated electron systems, like PCBs are great for electron capture, but the PFASs do not have conjugated electrons. Other PFASs in general are not volatile enough for gas chromatography, but the carboxylates can be derivatized. Methyl esters are very easy to make. The sulfonates, however, cannot be derivatized. If you look at the electron impact mass spectrum of the PFOA methyl ester, we see that most of the response are in very small pieces at very small masses, and that's kind of buried down in the weeds. You don't even get a molecular ion for this thing. So GC mass spec was generally not thought to be sensitive enough for the needs and could not address a big chunk of the PFAS family. With PFAS, we generally had to rely on ion chromatography with detection by conductivity. I'm going to assume that you're familiar with ion exchange columns where the ions are partitioned and separated from each other and from neutrals. That, however, is not a particularly sensitive or selective technique. So there was not a whole lot of trace level work done until post-2000. And that's when the electrospray interface for coupling liquid chromatography to mass spectrometry was commercialized, right around 1998. Before this, LC-MS was good for qualitative structure elucidation, but its quantitative performance was poor, and it wasn't particularly sensitive. But once the electrospray interface was commercialized, quickly LC-MS, which is tandem mass spectrometry, became the analytical tool of choice for determining low levels of PFASs in environmental samples as well as human blood serum samples. So real briefly, LC-MS involves, first of all, chromatography, separating by polarity and solubility, then a quadrupole to separate by mass. You then hit it with high energy argon or nitrogen and break it up into characteristic fragments, and then you separate the fragments by mass once again, and you measure the signal that it corresponds to the first mass, which is usually a molecular ion, fragmenting to a specific second fragment mass, precursor to fragment. And this is gives you excellent sensitivity, excellent discrimination from chemical noise, and really a very quantitative, reproducible analysis. So looking at this a little bit more, the PFAS is determined in environmental biological samples exist as anions, both the sulfonates and the carboxylates. Sulfonates, of course, have a pKa around 0 or less. Carboxylates have pKa's that are generally lower than the corresponding carboxylic acids because of all the electronegative fluorines on there. So therefore, we use negative ion electrospray. In this case, we're going to bring in our ions using this little figure I have in the top right corner. Bring in our ions, form a spray. They form charged droplets. We're hitting it with heated nitrogen gas. The droplets become smaller and smaller by evaporation. As we cram all the negative charges together and the solvent goes away, a Coulombic explosion occurs, and this process happens over and over again until we get a gas phase ion. You have to make a gas phase ion in order to detect by mass spectrometry, otherwise you will not see it. So the way this works is that the precursor to fragment selection we get in the tandem mass spectrometer plus your HPLC retention time is extremely selective for PFAS analytes. Now we have an excellent rejection of interference and chemical noise, and as a result, once people started applying this technique around the turn of the century, that's when we realized we had a problem with ubiquitous PFOA and PFAS in the environment, soon followed by others. We were even picking this up in, say, polar bear livers from the Arctic region. But let's focus on drinking water now. Most likely, the leading analysis in the environmental PFAS field, and the one that we get most of in my lab, is drinking water related samples, either finished drinking water or raw drinking water that's going in for processing. Most of the water companies require reporting limits around 1 to 2 parts per trillion in their finished water product. EPA has a health advisory level of around 70 parts per trillion, but the states where they are moving on this are typically in the single-digit part per trillion for finished water. So this type of analysis is called a targeted analysis. In a targeted analysis, you know what analytes you're looking for. You have authentic analytical standards of each, and that helps for both verification and quantification. And as a result, it's a narrow subset of PFASs. So a trace level PFAS water method looks like sample collection, sample preparation, measurement, and data processing interpretation. And there are challenges in each step that can often be unique to PFAS analysis. When you select an analytical method, it's best to have a standard method that's standardized across multiple labs and recognized by the regulatory agencies. Currently, there's only 2 such methods for drinking water, EPA method 537.1 and 533, and you see they're both fairly recent. There are other non-standard methods out there. They are called EPA 537 modified. Every lab has their own version of EPA 537 modified. That can mean anything. It's often used for non-potable water samples, but it may not be recognized by relevant agencies. The older method, 537.1, the emphasis on legacy compounds, the ones that have been out there for a while. So you have the C6 through C14 carboxylic acids, the C4, 6, and 8 sulfonates, then some replacement chemicals, a couple of wetting agents, compound F53 major and minor from China. Adona is 3M's replacement for PFOS, and Gen X, I mentioned, DuPont's replacement for PFOA. And then a couple of precursors that degrade to PFOS in the environment. Notice I've starred short-chain PFOSs here, and there's only a couple. These are mostly long-chain PFOSs. So EPA method 533 comes along and complements that with more emphasis on current compounds. There are shorter chain carboxylates introduced, the C4 and C5. We have a full range of shorter chain sulfonates. The replacement chemicals are the same. Now we have some fluorotelmer sulfonic acids that are very important, and you see them a lot in the environment. And then we see some of these chemicals coming in that mostly show up in industrial areas where PTFE and other fluoro products are manufactured. They're rarely seen in the general environment. So the EPA health advisory level is 70 parts per trillion combined for PFOA and PFOS only. These are not regulated contaminants yet on the federal level. We recommend that reporting levels be at most 2 to 4 parts per trillion for drinking water analysis, and that's covering some state regulations now. And the health advisory level is going to be the sum of multiple PFASs. Single-digit part per billion or nanogram per gram levels seem to be sufficient for other sample types like the non-potable waters, soils, sludges, and sediments. Potential technical issues are contamination. We see PFASs coming in from fluoropolymers, coatings, laboratory contamination, and so the result is that you get false positives and high reporting levels due to the background that's present in your blanks and in your laboratory. Recovery is not so much an issue, spiking in and recovering the PFASs that are there in a sample. If you're not doing standard concentration methods, they may not extract all the PFAS components, especially short chains, which are difficult to stick to some SPE cartridges. The long chain compounds, on the other hand, might stick to sampling containers. This is a case where a nonstick compound becomes sticky when you don't want it to. It can be pretty frustrating. In sample collection, there's a huge potential for contamination from the sampling equipment itself, clothing, cosmetics. Really easy to contaminate something at a part per trillion level. The solution, or at least the monitor, are blanks. So the sample collection bottles should have been provided and tested by the laboratory, and then we normally include 2 bottles filled with water known not to contain PFAS and give that to our customers. One is a trip blank. It just travels with the samples. The other one, water is transferred to an empty bottle, which we provide at the time the samples are collected. This will at least tell you if contamination was picked up in the sampling process or in the sampling containers themselves. Sample preparation is done by solid phase extraction. And so here's your classic SPE setup with the vacuum manifold. Our sample is in a 250 ml bottle. Typically, the sampler lines going to the SPE are made out of PTFE, so we have to replace those with polypropylene. There are PTFE liners inside there. We have to pre-soak those in methanol to get out any PFASs. And so that's how we cut down on lab contamination. So we replace PTFE wherever we can. Single-use polypropylene labware for everything, including the auto sampler vials. And there can be carryover from high-level samples, so typically we have to trash a lot of these sampler lines and replace them when we do high-level samples. The 537.1 method requires a neutral polymer styrene divinyl benzene sorbent. No copolymers allowed. The 533.1 uses a weak anion exchange sorbent in order to better catch the shorter chain compounds. And we do more blanks during the process. We carry PFAS-free water through the entire procedure and analyze it for background levels. And then we, at the end, we have to use a solvent rinse of the sample container, this 250 ml bottle, to catch any long chain compounds that were attached to it or stuck to it and get that back into our extract. Here's a graph here I did at the bottom, just looking at recovery of different PFASs, where I spiked water at 300 parts per trillion with the EPA 537 analytes, shake it for an hour, and then direct injected the water, and you see that I recovered 100% of my short chain compounds, but it really drops off for the long chain compounds, and I essentially lost my C13 and C14 carboxylic acids. Soil, sludge, and sediment. The samples are straightforwardly extracted with methanol. We use dispersive solid phase extraction, so we have some granular activated carbon. We just shake a little bit of our extract. You see it goes in this picture from a colored extract to a clear extract, and we get rid of a lot of contaminants, interferences, matrix suppression compounds, and all that. Again, we use single-use labware, and then we isolate everything from our concentrated standards. We'll carry solvents through the procedure and analyze for background levels just to make sure that we've gotten everything. By LC-MS-MS, we analyze the usual way. Keep in mind that there are PTFE components in common LC-MS-MS instruments. The solvent lines are typically made out of PTFE. You have PTFE tubing and parts in your pump, and so that is a real challenge. You can replace some of them, but not all of them. So I reported the use of a delay column back in 2005. This is a column introduced between the pump and the injector, as shown down in this picture at the bottom. And what it does is it catches any PFASs coming from the instrument itself and holds them up just a little bit and gets them away from our analyte peaks. Andrew will talk more about that later on. More blanks, instrument blank. We blank it after each series of calibration standards, after QC samples, after each known high samples, by just injecting dilution solvent. Optimizing the data acquisition. For LC-MS-MS, we don't worry too much about selectivity. I choose A and B mobile phases to yield the best sensitivity. If at all possible, I'll use methanol instead of acetonitrile just for the expense. So this little table for MPA and MPB, we see 2 common choices of MPA, 2 common choices of MPB. I use ammonium acetate methanol. That seems to give similar sensitivity to acetic acid acetonitrile. Your runtime and gradient steepness, you can save some time by letting the mass spec sort out things for you, but especially when you have a clean sample. Coelution is okay. The mass spec will resolve different compounds from each other in mass. But the dirty samples can lead matrix suppression. That's what happens when you're forming a droplet and there's charged species appearing on the outside that don't let your analytes out of the droplet before it goes to waste, and it doesn't end up in the mass spectrometer. Let the column do its job in this case. Here's a chrome I ran years ago where I held the analyte on the column for 4.5 minutes. I got a certain peak height. After only a little bit more time on the column by making a weaker mobile phase, I got a much higher peak. Then there is a requirement for peak symmetry. The asymmetry factor must be between 0.8 and 1.5 for the first 2 eluters in EPA methodology. You have to have your injection samples in 96.4 methanol water. So here's a couple problems or a couple examples where I used a fully porous C18 column and a porous shell column. And both of them worked very well for 2 very early eluters, the C4 and the 3-methoxy perfluoropropanoic acid. Both gave acceptable peak symmetry values, and the only caveat was that the initial mobile phase for the porous shell column had to start at 20%, and it could be 40% for the fully porous column due to the more carbon loading that's present. But the porous shell column gave perfectly acceptable performance, just maybe a little bit more time, but no big deal. With large volume injections, you can make direct injections of 100% water samples if you're only concerned about the short chain compound. And here we're seeing some of the short chain compounds come off very nicely at single-digit part per trillion levels. The butanoic acid, butane sulfonate, branched linear for PFOA at 11 parts per trillion, PFOS branched linear at 15 parts per trillion. But remember, if you're direct injecting just water, you have lost your longer chain compounds on the sample collection container. So that is my talk, and thank you very much. I now turned it over to Andrew.
Chuck. Okay, thank you so much. So we're going to talk a little bit about now from actually AMT side. We're going to talk a bit about the columns and some of the applications that we have for you. So, what is the HALO PFAS solution? Well, the HALO PFAS solution is an application-assured column solution. It consists of a delay column, which is used to prevent, as Chuck mentioned, the background PFAS contamination. from interfering with the PFAS of interest that are separated on the PFAS on the analytical column. So there's two columns. One's a delay and one is the analytical column. The delay column is a bonded phase, which is a highly retentive SPP encapsulane chosen for its ability to demonstrate high retentivity across multiple mobile phase conditions. The analytical column is a bonded phase. It is an SPP N-capped ODS. And the major difference between the PFAS column and a regular C18 is that the Halo PFAS solution, in that it's quality assured for PFAS analysis, providing the customer the confidence it will meet their application demands with a delay designed to prevent interference from background PFAS. So as we look at this schematic, and as Chuck had mentioned before, PFAS are forever chemicals, and they are all over the place. They're even in your HPLC. They're in the tubing. They're actually all over the place. And there are many challenges for being able to analyze these things. So after you go through all those steps to get the solution, or to get the sample to your lab without cross-contaminating, you have the whole other issue of cross-contaminating with your instrument. So if we look at this setup, we put the Halo PFAS delay column in between the mixer and the sample injector. And the purpose of this is to just delay the PFAS that are going to be coming off of the HPLC from the tubing, from the various connections that are inside there that are made with substances that do contain PFAS chemicals. So the Halo PFAS delay column sits in between the mixer and the sample injector. It has its interaction with the mobile phase as it's flowing through. It catches the PFAS, it delays them, and then we do a sample injection where we do the separation of your sample without the contamination associated from the instrument. So here's a little example of the delay column effectiveness, showing the delay of PFOA contamination by 0.7 minutes. So we have the analyte peak, PFOA, and then we have about 0.7 minutes later we have the contamination peak from the HPLC. Now, as actually Chuck had said before, one of the easier things about this method, there aren't many things easy about PFAS analysis, but one of the forgiving things is that you can set your windows. So for sure, we have basically this column which can separate on the analytical column, and then we can use the delay column to move away the contamination. So we can set our window where we will never see that contamination from the HPLC. So that's one of the workarounds for it, and it is a very good way to do it. Okay, so a little bit about the application methods. EPA 537.1, Chuck had mentioned, this is actually for the drinking water supply in the U.S., and it has 18 compounds, and it was one of the first methods to quantitate PFAS that was introduced by the EPA. And actually 537 was introduced before, and then it was amended to 537.1. And we can see that we have the 18 compounds, and they're separated in about 15 minutes, and it's a pretty good separation. We have a pretty clear separation of all the components. And what I should mention is that we wanted to, when we were working with these columns, we wanted to make these columns very universal for all EPA methods. So we stuck with the same method that we came up with to run actually all the existing EPA methods that we could get samples for, that we could get standards for. So as we mentioned, EPA 537.1, this is for the drinking water samples, and this is for longer chains. There's a couple of short chains on there, but this is for the longer chain ones. And then this is for the short chain, EPA 533. So there's 25 compounds in EPA 533. And again, using the same method, we were able to separate them very easily, very quick separation, using the same gradient, same mobile phases, same injection volume, same sample solvent, everything like that. So we were able to run both 537.1 and 533. 533, the short chains, which is drawing a lot of interest because once the EPA started to find that once these companies started to see, okay, well, PFASs are a little bit of a problem, the companies switched from making long chains and started to focus more on short chains. So short chain PFASs became more prevalent in the environment, and so we have to focus on analyzing them as well. So EPA method 533 was introduced, and these columns are able to do EPA method 533 very well. Okay, another method that has been developed and validated, I believe, by the EPA, I might be a little bit off on where it stands officially, but it will be introduced soon, it will be made law soon, is EPA method 8327, and this is for non-potable water or for wastewater samples. So this is going to be also involved with biosolids and everything else like that. So this, again, are compounds that are found in EPA method 8327, non-potable water, and the actual 24 compounds that were in there, we were able to separate them as well using the same method. Columns performed very, very well. This is all done in under 15 minutes. The separation is done in under 15 minutes, so it can be improved, but we wanted to keep a standard method to go through all of the EPA methods to make sure that these columns could perform in each one of those methods, and they can. Okay, so applications, branch versus linear isomers in well water, and spiked well water. So as Chuck had mentioned, there's linear isomers and there's branched isomers, and this is an example of the separation between the linear and the branched isomers of PFHXS. And as actually any mass spec guy will tell you, you don't need, as any mass spec guy will tell you, the only thing that you need the chromatography for is to just run the sample. Well, you don't, because if two things weigh exactly the same, no matter how sensitive your mass spectrometer is, you won't be able to separate them. So you definitely need chromatography, definitely need the front end, and you definitely need columns that are able to perform and be able to separate these isomers that are found in here. And you can see these columns can definitely separate the branched and the linear isomers of the PFHXS. Okay, so if we want to think about this for a second, so how can fused core benefit PFAS separations? And one of the things that we want to think about is not necessarily now, but in the future. So the answer is simply speed, and that's straight off the bat, because as the technology continues to progress, mass spectrometers will continue to be improved in regards to the level of sensitivity, mass resolution, and scanning speed. And this will undoubtedly impact future developments in PFAS analysis, and column performance must be able to handle these advancements. It's very likely that more and more PFAS compounds will be added to methods in the future, where as soon as we find them, we start to test them, we look at the toxicology of them, and then we're going to have to start to add them to lists to be analyzed and quantitated. So with this in mind, we developed a method for the separation at maximum speed to test the suitability for the columns to use in these advanced conditions. So the higher scanning speed of the MS instruments will lead to faster analysis time and higher flow rates. But negative effects are often associated with that, and often an increase in the speed of analysis will lead to a decrease in the resolution, therefore causing coelutions. But as we can see with these compounds here, we separated 33 components, PFAS components that are found in 537.1, 533, and 8327. There is going to be some cross-pollination between these methods because there are similar compounds. There are exactly some of these methods have the same compounds in them, but you're able to see that we're able to separate these 33 compounds in below 5 minutes, and in a pretty good, easy to analyze spectrum. So one of the advantages of SPP technology and fused core is to be able to run at high speeds and have high resolution separation. So we wanted to take advantage of that, and not necessarily for now, but in the future, as more and more compounds get added and more labs need to run samples, we wanted to be able to provide our customers with the option that, hey, these columns can perform at these high speeds. They're more than ready to accept that challenge. So a quick comparison of the 18-minute gradient to the 5-minute gradient, and you can see that it's an average of 2 to 3.5 times faster, and no loss in sensitivity or the resolution. We can ID them all, we can separate them all, and the comparison is a good EPA 533 because those are the short chain ones, which are very problematic right now. So we wanted to get ones that were very, very problematic. Okay, now reproducibility. How reproducible are these columns? How rugged are these columns? So we took the FAST method that we developed, and we looked at just EPA 537.1, and we did about 300 injections, and we can see that we have the shift in the retention time was on average of 0.023 minutes. So very reproducible over 300 injections, very robust, very high performing columns, and they are very, very, without being biased, it is a very good system. It works very, very well. We'd like to acknowledge Dr. Charles Pally from Stride and for PFAS Solutions for our help before and for also being on this seminar with us. And that's the end of the presentation, and I would like to turn it back to Laura, who will have a couple of, I believe, survey questions for you, and then we can begin the Q&A. So thank you very much.
Yes, thank you very much, Andrew and Chuck, for your informative presentations. We do indeed have a couple of questions for everyone in the audience. So we have in each case, you can click directly on your screen to enter your answers. And that first question is now up on the screen, and it says, would you be interested in learning more about HALO and ViraClass columns, yes or no? So again, you can click directly on your screen to answer, and that question is, would you be interested in learning more about HALO and ViraClass columns, yes or no? Fantastic, thank you. And now we'll go to our next question. Line that up for you. So that next question is now on your screen, and again, you can click directly on the screen to answer. And it says, do you feel that you learned something new about environmental separations or method development today? Yes or no? So once again, do you feel that you learned something new today about environmental separations or method development? Excellent. Thank you very much for taking our 2 polling questions. It is now time to go to the question and answer session. We have a little bit of time to get a few questions in. As a reminder, if you'd like to submit a question, you can do that by typing it in the Q&A box, and you can find that on the right-hand side of your presentation window. All right, so we have a few questions that have come in, so let's get a couple going. So here's one. I think this is for Chuck. Are there any PFC contaminants found in foods?
Yes, I kind of alluded to that. So you can get PFC or PFAS contaminations in foods 2 ways, at least 2 ways. One would be from the packaging materials. The other would be with this waste treatment sludge that is applied to farm fields, and typically then that shows up in grass and hay that's fed to cattle, and we've seen instances where the PFASs then show up in the resulting meat and milk. So those are a couple of examples where PFASs are found in food, and that is actually turning out to be an emerging important source of PFAS exposure to humans.
Sobering. Thank you. Can you inject more than 2 microliters and retain peak shape with 9604 samples?
So, Andrew, did you want to do that one?
Yeah. So with actually more than 9604?
Well, it just says with 9604.
Well, the big question would be the peak symmetry. So if you can get your peaks to pass the peak symmetry and be within that range of 0.8 to 1.4, and it's for the first 2 peaks of your run, then yes, you can. There have been, but certainly there have been modifications on this method where people have done injections and actually done this method without actually 96.4 and have been able to do it well. So yes.
Great, thank you. Andrew, I think this next one's for you too. 300 injections in what period of time? If the LC is in standby mode, would that pose any problem?
Well, that's a good question because you can have a buildup of PFAS over time. PFAS will build up over time. So this 300 injections was done it was done all day actually. So I actually did begin the run at 6 in the morning, and it was done a little after 4 in the morning the next morning. So we didn't see any major change or major increase in the actual PFAS. And so we didn't see any buildup in the PFAS over time, and we didn't see any major shift in the retention. So in terms of was there an increase in the intensity of the signal, there wasn't a noticeable increase in the intensity of signal. Now, if you tried this over more than a 24-hour period, it's possible because there have been cases where PFAS does build up over time through the instrument. Specifically, it would begin to leach out of the plastic that's inside the instrument. But the adequate performance of the delay column didn't show any major increase in intensity or shift in the retention time over that period of time. So that was about a 22-hour period.
Thank you. What concentration levels of internal standards do you recommend for biosolid extraction?
You want me to do that one?
Yeah, sure.
Okay, so with biosolids, our quantification limit is 1 part per billion. And so I typically like to have internal standard concentrations in about the middle of my calibration curve. My calibration curves tend to be a bit narrow in range, so I might run my internal standard fortifications at around 5, 10 parts per billion.
All right, thank you. How can you eliminate PFAS accumulation in the LC system?
Well, that's very difficult. As a matter of fact, that might not be possible because there are parts of your instrument that are actually made with compounds that they are made with tubing, they are made with different types of plastic that do contain PFAS in them. So the way to mitigate that, I mean, there are certain things you can do. You can try to swap some of your lines. You can try to swap some. I've even seen people that have actually tried to swap some have actually. One person tried to swap the head of his pump, and that didn't work out well. And that was for a totally different reason. But it's almost impossible to completely eliminate PFAS contamination from your instrument. So that's why it's so essential to have the protection of using that column to actually delay before you do the injection of your sample.
I would just add that there's also can be traces of PFAS in your mobile phase solvents as well, and your delay column will take care of that.
Excellent. Well, with that, we're out of time, so we'll need to wrap up. So thank you both very much for your talks today and for answering all those questions. I also want to thank everyone in the audience for attending and participating in our event today, and I'd like to thank our sponsor, MacMod, for making today's webcast possible. You'll receive an email alerting you when this webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.